Okay, so only 2 people have joined. Let's wait for a couple of more minutes to see if anyone else joins. Meanwhile, if you have any doubt regarding previous session, you can ask. I think I had only Ananta joined yesterday. Ashwin is new. So Ashwin, where are you from?
Hello, sir. Am I audible?
Yeah, you are audible.
Yes, sir. I am from VIT, Vellore, sir. Tamil Nadu.
Vellore.
Yes.
Okay, VIT.
Yes, sir. VIT, Vellore.
So which year you are in?
Now, currently, I am doing MTech, sir. MTech in VLSI, second year.
Oh, MTech in VLSI. So what is your thesis topic?
Uh, Actually, I have submitted a topic based on folk sheet fit, sir.
Okay, Fox sheet fits. Okay, fine. So you are going to do TCAD analysis or anything experimental?
No, yes, sir. We are performing based on a ticket, synopsis, centers ticket.
Centaurus TCAD. Okay, fine. Okay, so let's begin actually. If other people join, they can catch up. So welcome. This is NOC 26 86 NPTEL tutorial session on semiconductor devices for next gen FETs, more than more, a physics perspective, right? The course instructor is Professor Sudeb Dasgupta from IIT Roorkee. I am Debashish from IIT Kanpur. So as you know, we go live every week from 3 to 5 on Saturdays. So it will be a 2-hour session. So if you have any query, you are free to stop me. Okay. What I plan to do is to fill some gaps in the concepts. Okay, by means of problem solving. So treat me as a peer and your fellow student so that we can have discussions, and by those discussions we can uh, basically clear up some concepts. I may not be knowing everything, but if you ask me good questions, I'll be really happy. Yeah. So let's start. So yeah, yesterday I stopped at MOSCAP band diagrams, right? MOSCAP is basically a two-terminal device. So I have discussed how to draw the band diagram. What are the things we should be focusing on, right? So today what I plan to do, extend that discussion towards multiple regions of operation, right? So your MOSCAP will be something like this. This is your, it is a two-terminal device. That means you can apply voltage or probe current in these two pins only. This is called gate. This is called body or substrate. So we discussed with the p-type silicon devices, silicon substrate, metal oxide, semiconductor. So this is the, we call this view a cross-sectional view, right? Cross-sectional view. So actual device is in 3D, right? So there will be another direction. So it will be something like this, the actual device. And what I am looking at, this, let's say, only this rectangle. But that is from the physics point of view what we'll discuss, because there only all the physics are lying. And what we assume that, so this is your length direction, this is we called depth direction, or let's say your vertical directions, and this one is your x, y, z. This one is your, okay, let me follow right hand thumb rule, right hand rule, so it will be like this. Let's take this one x, this one y, and this one z. So it is your width direction, right? So you will see that width direction is important when you go into MOSFETs and all, some narrow width effects and all those. In those cases, it will be important. So what are the assumptions in our discussion? That
Sir,
yeah,
sir, but there's a problem with this particular convention of XYZ because if we take that right hand rule, won't the Z be pointing in the opposite direction to what you've drawn?
or you meant to say this will be minus z?
Yes, sir.
Okay, that is fine. We can have that translation. You are right to point that out. So let me take this is, how do you propose then? Let me take this one x, this one y, then also I'll have that issue, right? Let's take this one y, this one x, this one z. Is that now okay?
Yes, sir, that's okay now.
Fine. So, by the way, who told me that?
So it's me,
Ananta,
Anand.
right? Yeah, yeah, yeah. Good,
Yes, sir.
good one. So everything along width direction is uniform. Okay. That means I can slice that MOSCAP and take one cross section, and if I do the analysis there, everything we can just multiply it with W in that direction, Z direction, and everything will come out to be just a scalar multiplication, what I mean to say, right? So this you need to be very careful about. But what I was pointing out that when you are in industry, when you will be, let's say you want to fabricate this. So this, let's say your MOS capacitor, you want to use it as a some kind of voltage dependent capacitor. It is ultimately that, right? So it is kind of an your variable capacitor, varicap or varactor. Now you want to tape it out or get it fabricated to some industry company, let's say some fabrication unit, let's say TSMC. So what will you send to them? You will send to them only this portion, this rectangle, okay? And your design will look like this. So it is something you are looking from the top, let's say EF. So this is your length, this is your width. So if you, I do not know if you have seen any inverter layout and all, we call it inverter layout and all, it only comes in some rectangles, right? You will not be able to see anything else apart from rectangles. Have you seen any of such cases? Your entire MOSFET designs and circuits will be something like this. this, another block, then you will have some joinings, right? It will only be rectangles. So when you see some layout, so don't get confused with the dimensions. In that case, you are talking about the length and width direction only, right? Because whatever happens in this direction or y direction is taken care by the fabrication unit or fab, right? The circuit designer, for example, you want certain amount of current through a MOSFET, so you need to fix on the length and width. So the circuit designer or the IC designer, integrated circuit designer, has the degrees of freedom of only W and L. Everything rest is determined by the foundry, and they will give you something called PDK or process design kit, where every other details will be mentioned by some numbers, right? Some real numbers. Okay. So if that is done, so what we generally study, as we are interested in the physics, so this course is a physics perspective. Wait a second. So as this course is a physics physics point of view we are discussing, so we are concerned with only whatever is happening in y direction, right? So that is why we'll just take a cross section take a line in this direction and discuss the band diagram. Fine. But in case of MOSFET, your current flows into the length direction, then we will use make use of the x direction as well. We'll see. We just it will not be enough or sufficient for us to draw band diagrams in this y direction, but as well as we need to understand how the band diagrams at x direction looks like. Fine. For MOSCAP, we are concerned with only y direction. So as you know, generally we just flip the device and we draw the band diagram in this fashion, in this way, right? This is, let's say, gate terminal. This is your body terminal. Let's say this is P type. So I will draw a couple of lines. So let me just draw two real number lines. This is some real number lines, okay? In one case, I am concerned with VGB. In another case, I am concerned with psi s, the surface potential. We'll define that, okay? And we'll mark the regions. Fine. For our discussion, we are assuming phi ms to be 0, qox to be 0. That will lead me my flat band voltage to be 0, right? So let's say this is a voltage that is 0 volt. Fine. Now let us consider a case when my VGB is less than VFB and try to draw the band diagram. Fine. So first thing, we'll draw the separation, or we call it the junctions, heterojunctions, right? This is MOS. Fine. So what is the first line I should draw if I want to draw something in VGB non-zero value and less than VFB? That means negative in our case because my VFB is 0. So what is the first line I should draw?
Vacuum level.
No, not vacuum level.
So Fermi level.
So vacuum level we draw when we have the devices disjointed. I'll come to that. What do we mean by vacuum level and what do we mean by local vacuum level? Okay. What we draw generally is local vacuum level, not vacuum level that means at infinity. That we do not draw generally. We draw just outside the device that we call local vacuum level. And the reason for that will be clear from this discussion. So let's say first I draw metal Fermi level and let's say semiconductor Fermi level. Why do I draw like that? This is EFS. Let's say this is EFM. So EFM is basically your EC and EV as well for metal that we have discussed last day, right? So what is the separation? Can you tell me? What is the separation? Any idea?
So 5 ms.
No. I have assumed 5 ms 0, right? Anyone? Ashwin or Minakshi?
Or whether it is a half the band gap energy.
No. So by the way, tell me what is Fermi level? So first thing, what if I had these two portion connected? That means what? My VGB is 0, right? Is that clear? If my VGB is 0 and my phi ms is 0, then both the Fermi level should be on the same line, same level that we have discussed yesterday. Now what I am doing, I am increasing the gate voltage with respect to the body. So what I am doing essentially, physically what I am doing, I am, let's say my VGB is negative, right? That means with respect to body, my gate voltage I am increasing, I am decreasing. So gate voltage decreasing means what about the Fermi level of the metal? Is it going up or down? Understand that Fermi level defines or determines the average electronic energy in the system. Fine. Now I am applying negative voltage at the gate. So what will happen? The average electronic energy will increase or decrease. Anyone? See, this is very important to understand these concepts, okay? So once you are done with this, then everything will be smoother. So it is better that you speak up and let us have a discussion. If it is not, if your concepts are not there, we can have a discussion and it will be there after the discussion, right? So my question is, suppose there is a system. Let's say there is a glass bowl where some electrons are there at some different energies. So all the electrons will have at some average energy. You will sum all the energies of each electron and divide it by the electrons, right? Now what I am doing, I am making that more negative. So will the electrons energy increase or decrease? Anyone? Okay, just tell me this thing. What is the x-axis in the energy band diagram and what is the y-axis? What is the x-axis and what is the y-axis in this diagram? Ashwin, care to answer? Am I audible by the way?
Sir, y-axis is the energy difference.
What is x-axis? What is x-axis? It is you can just look at the diagram and tell, right? X-axis is distance along the system, right? You can see that it is distance. I am going from metal to oxide to semiconductor. Fine. And what about y-axis? Y-axis is nothing but your electronic energy.
Yes, sir.
So electronic energy relates to potential how? It is
VG by
minus of q times potential, right?
yes, sir.
Now I am now I am decreasing my psi. What will happen to electron? What will happen to energy? Energy will increase, right?
Yes, sir.
So in energy band diagram, if I apply some positive voltage, my energy decreases because I am talking about electronic energy. Fine. And if who is joining? And if I am applying negative voltage, my energy band diagram shifts upwards. That means my electronic energy increases. Of course, right? If at that negative terminal of the battery, I will have a more electronic energy than in the positive terminal because the negative terminal injects electrons. You can think in this line as well. Fine. So if I apply negative VGB, that means my gate is at a negative potential. That means the electronic energy at the gate will increase. That means my Fermi level at the gate will increase. So this is what is happening. This gap is nothing but Q times VGB. This VGB, that VGB less than 0 I am applying at the gate. Is that clear?
Yes, sir.
So again, then what is the next step? I need to draw the bands, right? So for metal, what band do I have? I have only vacuum level E0, and this E0, this gap is a material property, metal work function Q phi m. So it will be fixed, right? And in case of semiconductor, as it is a p type, so I'll draw the conduction band and valence band. Once I draw my conduction band and valence band, and this gap, remind you that this is fixed irrespective of doping and all, because this is Eg band gap. It is property of the silicon. How much you can dope it, it is not going to change. Why? Yesterday I have told, right? in 10 to the power 7 silicon atoms, you will be having 1 to 10 dopant atoms, right? So the material remains silicon. It is just that you are tuning the properties of the material by means of doping. So then if EC is known, then you know your, what do you know next? You know your electron affinity, right? That is also a material property of silicon. So let's say this will be your E0, and this is determined by this gap Q chi. Fine. Now what is the next step of the band diagram? What do I need to consider next? I need to join these bands, right? Somehow.
Yes,
What
sir.
is the next step?
So we need to align the Fermi levels.
No, Fermi levels. Why will you align? The difference of Fermi level is the potential that you are applying. So if you are applying your potential VGB, which is non-zero, Fermi level will split, right? Between metal and semiconductor, there will be a gap in the Fermi level. That is the potential you are applying. That is what we have discussed, right? Is that clear?
Yes, sir.
So next step is you need to understand profile of E0. So you have a metal, then a semiconductor, then an metal, then an oxide, then an semiconductor. Fine. This is the physical device, let's say. So where is your Fermi level? Where is your vacuum level? Your vacuum level is somewhere here on top of the entire system. It is not part of the system, right? So condition on vacuum level is E0. It is called local vacuum level, and E0 has to be continuous. E0 has to be continuous. Okay. Other bands can have discontinuity. Yesterday we have seen if we have a heterojunction, there will be discontinuity between bands. Fine. But E0 always has to be continuous. Why so? Because you know what is your electric field. Electric field is minus d psi by dx. This d psi I can write minus E0 some reference energy, let's say, divide by q, this relation. So it will be nothing but 1 by q dE0 by dx. What will happen if E0 is discontinuous? What will it will lead to? My electric field will be infinity or some kind of delta function. If your E0 is something like this or something like this is continuous. Okay, let's take this example only. This is discontinuity, right? You are aware of limit and continuity, right? So what is the what will be the electric field profile? If this is with respect to x, E of x will be E of x will be a delta function at this point. What is the magnitude of that delta function? Minus infinity. So do you think there is something in the physical world called infinite electric field? Anyone? So infinite electric field is not possible, right? So that is why my E0 has to be continuous. Fine. So that means this will be, just don't ignore about the profile, just understand that E0 will be something like this. Okay, that I'll come to how this structure came into place. It will be something like this, E0. So in this case E0 is continuous. Okay, that means left hand side limit and right hand side limit are same. In this case it is not. Fine. And now, as let's say I am in this diagram, I am only concerned about the semiconductor. So throughout the semiconductor, my Q chi and Eg will remain same because it is silicon. So other bands will just follow the E0. Okay, and Fermi level will be remain constant because there is no current flowing through the insulator. Fine, is that okay? So if that is the
Yes, sir.
case, then you can draw the, similarly in case of your insulator as well, it will follow the E0, EC and EV will follow the E0 of the insulator. So this will be the band diagram in case of VGB is negative, right? Now there are a couple of things we need to check. So first observation point is that you see that EC has discontinuity, right? EC has discontinuity because EC is inside the material. EC I am, where is my EC? EC is inside the material. And if I go from metal to semiconductor, I am seeing three different materials or hetero junctions. I am crossing two hetero junctions. So that is why EC will have discontinuity. But in case of E0, I am seeing only vacuum or air, right? It is the same material. So that cannot have any discontinuity. If you have done your electromagnetics course in undergrad, you must have seen that if there are two materials, material 1 and material 2, the normal component of the displacement vector is continuous, right? That is one boundary condition we used to, whether you have studied Sadiku's book or Nathanida's book, you will see this, right? And
Sir,
what does that mean? That means epsilon
electric.
1 electric field 1 is equal to epsilon 2 electric field 2. So if your epsilon 1 and epsilon 2 are different, so of course your electric field will be different, right? So that is what it is happening. Another thing to note that I am drawing linear band diagram in SiO2. Why is so? I am assuming no charge is present inside the insulator, right? If no charge is present inside the insulator, so I know this is my d psi by dx is equal to minus d psi by dx is equal to electric field. And what does your Gauss law say? Your Gauss law say dE by electric field by dx equal to charge inside divided by epsilon. Do you know this is Gauss law?
Yes, sir.
So you can write your Poisson equation that d of psi dx square is equal to minus rho by epsilon. Now if rho is 0, in this case no charge is present, right? Rho is 0. So how will your d square psi by dx square is equal to 0? Then how will your psi look like? Just tell me the profile. If you integrate once, you will get electric field, right? That is constant. If you integrate again, you will get your potential. If what do you get if you integrate a constant?
We'll get a linear function.
You get linear function, right? That is why your psi is linear, and if psi is nothing but inversely proportional to, inversely means sign will alter, but it is proportional to your energy. So that is why your energy bands will be linear, because there is no charge present inside the oxide or insulator. This case will be different if there are charges present in the oxide layer. Okay, is it clear why it is linear?
Yes, sir.
Fine. So we are now at the location, this region, right? Negative VFB. So this negative VFB, negative VGB, this region is called, what is this called? What is this called? This region is called accumulation. Why it is called accumulation? What is the type of the semiconductor I had? What is the type of the semiconductor I had initially? P type, right? Will you agree with me that this distance determines how much P type my device is or semiconductor is? This distance, how close the Fermi level is to the valence band, is how much the device is P type. Is that clear? Do you know this thing?
Yes,
The
sir.
more the device is P type, Fermi level will shift toward the valence band, right? Or the distance will get reduced. So let's say this is 10 to the power 16, the doping. Fine? Or P type, P0 is your 10 to the power 16. What about in this case? What is happening here? At the interface, so this is called, so at the interface, is my device more p-type or less p-type?
So it will be more p-type.
It will be more p-type, right? That
Yes, sir.
means here what will I have? In this region, I will have accumulation of holes,
Yes, sir.
right? As majority carriers are getting increased at the interface, we call this region of operation as accumulation. Fine. So this is called accumulation. Another thing about surface potential, right? So we define a quantity. Let's say we have this line and this line. We define a quantity psi s equal to EC. Let me just reduce the size. So we define psi s equal to EC bulk minus EC interface divided by Q. So this becomes Q times surface potential. Okay. This region we call bulk and this is called interface, this part. So from this equation, can you tell me the sign of surface potential in accumulation? Is EC bulk lower than EC interface? This is EC interface, right? And this is EC bulk. So EC bulk is lower than EC interface. That means what? My surface potential sign will be negative.
Yes, sir.
So let's take a value that it is 0. So in this region, which we call accumulation, my surface potential is negative. Mind you, we are talking about NMOS only, where we have P substrate. Fine. Now what will happen at the flat band condition? At flat band condition, there will be no band bending. This particular thing we call band bendings. Okay. There will be no band bending in the semiconductor. That means what will be my surface potential at flat band condition?
0.
0, right? So that is why at flat band your surface potential is 0. This is corresponding to same line. Okay, VFB equal to VFB. That means at flat band, understand that your surface potential is 0. This you can get from your Poisson equation understanding as well. Bands are flat, that means psi is 0. Of course, this double derivative will also be 0, right? So that is your
Yes,
flat
sir.
band. Now we will go into the other part of the, we'll go into this part. There we will have multiple regions of operation. Fine. So let's say I am increasing my VGB greater than VFB by a small amount. So what will happen? So let's say this is my MOS structure. What is the first line I'll draw? I'll draw, let's say, okay, by one more thing. So you see that I had a band bending in the semiconductor, but I did not show any band bending in case of metal. Any reason for that? I could have drawn it like this as well, right? I could have drawn in this going this, then something like this, then something like this. So I could have had a band bending inside metal as well. So why didn't I have that? So let's say if you have a metal sphere, solid sphere, okay, and you are charging it with plus Q, let's say. Where will the charges lie inside the metal? If you,
So it will lie on the surface.
it will lie on the surface. Why so?
So because according to Gauss's law, charges cannot exist inside the conductor.
Right? Why so? You know about the concept of screening length?
No, sir.
You have not done EMFT?
So screening length in the sense, you mean the skin depth?
Skin depth, yeah. Electromagnetic wave, how much, how, metal is an ideal reflector of that, right?
Yes, sir.
Fine. So in case of metal, it lies on the surface, right? So if it lies on the surface, that means what is the net charge inside the metal?
0.
Your rho is 0. Fine. And what about electric field? Inside the metal, will there be an electric field?
No, sir. No electric field inside the metal.
Why not?
So because electric field is because flux of electric field is equal to the charge enclosed
Right.
inside the
But
field.
your electric field, if it is ideally spread across the metal, though the electric field lines will get cancelled, right? Inside the
Yes, sir.
metal. If you get resultant, your electric field will also be 0. So if
Hmm.
your electric field is 0, what is your potential inside the metal?
It will be a constant.
So your energy band will also be constant, okay? So this guy, if it is metal, if the MOS capacitor systems M is metal, then bands will not bend there because all the charges will be at the surface. So all the charges, in this case you had negative charges, right? All the
Yes, sir.
charges will be at this location. It will be kind of a sheet charge.
Hmm.
Okay. So now coming back to our discussion on the positive VGB. So if VGB is positive, so this is your EFM. So this will be your EFS. Is it correct?
Yes, sir.
Why is it correct? Your VGB is positive, right?
Yes, sir.
That means what? Your gate has a higher potential. If gate has a higher potential, its energy band should be lower to body or higher to body?
It should be higher to body.
It should be lower to body. It is electronic energy, right? Note this negative sign.
Hmm.
That is what I was discussing last time, this a couple of minutes back, right? If you apply positive potential, your energy bands go down. If you apply negative potential, your energy bands go up, because we are concerned with electronic energy. So
Okay, sir.
now I am applying positive potential at the gate. So gate Fermi level will be at lower than the semiconductor Fermi level, just the opposite case. In this case, I was applying negative voltage. So your this Fermi level will be higher. And what about this difference? Again, this difference will be sustained by this your QVGB, right? Is it clear with everyone? I hope it is, because this is one of the most fundamental thing you need to know before you go into any VLSI courses, okay? So now what? Now we'll follow the same steps. We'll start drawing this line as phi ms is same. So this is my E0. Then I'll have my EC somewhere here, EV somewhere here. Fine. And this E0 has to be continuous, right? There cannot be any band bending inside the metal, because all the charges are at the interface or at the surface of the metal. And in our case, the metal surface is this one. Okay. So no band bending inside the metal. And what about the insulator? It will have linear profile of energy because of no charge enclosed inside the insulator. So I'll have something like this. And this semiconductor band will bend to flush the E0. And what will I draw next? I'll draw EC will follow exactly E0. Why so? Because at this location it is Q chi. Similarly, at this location also it is Q chi, because it is a material property. Fine. Similarly, my EV will also bend, right? And let's say this EFS will remain constant because no current is flowing. Fine. So now I'll introduce another line. So that is my EI, or we call it intrinsic Fermi level, right? This gap is Eg by 2. It is not exactly Eg by 2 because your effective mass of the holes and electron in silicon is different. It will be slightly lower than Eg by 2 by around 13 millivolt. But we'll, for the sake of simplicity, we'll consider that this is Eg by 2, right? So this is also material property. This also will not change. So this will also start to bend. Fine. Let me just clearly draw this. So we'll have EF, and we will have EI. Okay, and let's say this is my EF. Fine. And similarly, inside my insulator, I need to draw. This is my EC. This is my EV. In case of metal, this is my EC. This is my EV. Fine. So what can you comment now at the type of this? Let's say, what can you comment at the interface? So let's say this is of course your P type. So what is the interface type now?
So it will be more like N type.
No. Why it is N type? In case of N type, where will my EF lie? Above EI or lower than EI?
Oh, it will lie above EA. It will no EA will lie above EF.
EI will lie above EF in our case, right? So
Yes,
it
sir.
is it
Type.
is still
P type.
it is still P type. Interface is still P type, but let's say weak. Okay, weak P type. So what is happening inside the in this condition? What is happening inside the MOS capacitor? So
So
this is
depletion
your
region form.
body, right? Start. What you are saying?
So depletion region gets formed.
Right. So this is P type, right? So what is happening basically? You are applying Vg greater than this. Let's say this is grounded. For the time being, Vb is 0. So my Vgb will be equal to Vg. So my Vg is greater than 0, or let's say more precisely VFB. We have considered VFB to be 0, right? If that is the case, what will happen? Positive charges will form at this interface, metal outer surface, right? This will start to create electric field lines. That those electric field lines will have to be terminated at some negative charges. Where can I get my negative charges in a p-type substrate? Where is that negative charge? What are the
Sir,
possible?
acceptable ions.
Right,
Sir, acceptable ions.
Na minus ions, right? And another possible charges is electrons,
Sir,
but those are
electron.
at very low value,
Yes, sir.
because
When EA crosses EF.
right.
Hmm.
So these negative acceptor charges, these electric field lines will get terminated. So let's say this is happening in this region, and this we call, let's say, XDEP, depletion. So what is the, we have used Y, right? So we'll use Y. So let's say this is Y depletion. So this Y depletion is basically this region. Okay, where your bands are bending. Why will the bands bend? Why cannot be the band flat? If the band is flat, that means my potential is also constant. That means my electric field is zero. But you can see that electric field lines are reaching till Y depth, right? So bands have to bend. Are you able to visualize? these are electric field lines which is not equal to 0. If electric field is not equal to 0, that means my d psi of dx, that is minus electric field, is not equal to 0. That means psi is not constant. That means minus q psi or E or energy is not constant. That means band bending, right? Note that
Yes,
below
sir.
this region you do not have anything, any charges or any electric field getting penetrating towards that below y depth, right? So that means what? Rho is 0. That means what? Electric field is 0. That means what? Bands are flat. You can see that in these regions your bands are flat. Is it clear? Is it clear?
So one more time, sir.
So let's say this is your y equal to y0, y equal to 0, this line, okay? And this is y equal to y depth. So if y greater than y depth, my electric field is 0.
Yes, sir.
That means my psi should be constant.
Mm.
That means what? My
That
energy
means
band should be constant.
yes, sir.
That means E is constant. So this line is y equal to 0. This line is y equal to y depth, and beyond y equal to y depth you can see that energy bands are constant, right?
Yes, sir.
And only in this region bands are bending, and this region is corresponding to this region, right?
Yes. Yes, sir.
So that is what I was trying to convey. So
Mm.
understand both the diagrams side by side, you will be able to get a more clear picture, okay?
Mm.
But remember, so far I do not have N-type interface yet. I still have a P-type interface, but it is going weaker and weaker. Fine.
Sir.
Now let's say what you are doing, you are keeping in, you are increasing, let's say increase VGB further, right? So if you increase VGB further, what you are basically doing?
So
Increasing
this
VGB
means that
means putting this line in which direction?
that will become more towards the down also down.
More downward. That means this will be more steeper.
Yes.
This bending will be more, right? You can
Yes, sir.
visualize, right? This bending will be more. So this will be more, this will be more. That means your EI will start to touch your EF and also can cross it.
Yes.
Okay. So let us take one case. Let's say this is metal oxide semiconductor. Now this is your EFS, EFM, your EV, EC, let's say this is your EI, okay, and your EI is touching your EFS. I'm just not drawing it in sequence. This will be your E0. So what is the nature of the interface now? The question is, what is the nature of the interface? Or surface? What type it is?
So now it's nearly N type. It's
Now
very
it is,
weakly, very, very weak peak type.
no, it is not N type, right?
No, it's very weak peak type. Very weak peak type.
No, your EI is touching Fermi level. What does that mean? What is EI? EI is, what is EI called, by the way?
Intrinsic Fermi level.
So if your EI is touching Fermi level, what do you call the device? It is intrinsic, right?
Intrinsic.
It is intrinsic. You see how my interface has become intrinsic now?
Yes, sir.
Now increase VGB further. We'll quantify this, okay? Just for the time being, take it qualitatively. So metal oxide semiconductor. So basically what we are doing, we are increasing this gap, right? We are increasing this gap. This is QVGB. So now I have drawn it a further larger, okay? That is what is meant by we are increasing QVGB. The Fermi level EFM and EFS are getting further apart and apart. So this is your EFM, this is your EFS, this is your EV, this is EC. Now who is calling it this? Now this is, let's say, EI. Okay. Now what is happening? Your EI is crossing this, and every other band will follow. So let's say here somewhere you have, okay, let's say here somewhere you will have your E0. This remains Q phi m. Okay. I should draw this E0 more towards this E0. So this is Q phi m. This is your Q phi m. So now what is the type? What is the type at the interface?
Now it is N type, sir.
Now it has started to become n-type, right? Okay. So what will happen at this point on the device? So earlier and all, okay, just let me do the dimensions. So this is y equal to 0. This is equal to y equal to y depletion, and this point at which my EC is crossing, EF is crossing EI, let's say this is y equal to YC. Fine. So in the device also we need to point out this is y equal to 0. Let's say this is y equal to y dep, and let's say somewhere here I have y equal to YC. Fine. So what I have done, I have applied VG greater than 0, putting VB to ground. So I'll have positive charges here, more number of positive charges, and that will get compensated by Na minus ions, right? And additionally, what will I have? Additionally, I'll start to have electrons. Okay, is that clear?
Yes, sir.
So now how will my field lines look like? Some field lines will terminate at the electrons and some will penetrate throughout till y depth, right? So this is my depletion region and this is where my electrons are lying. Fine. Is that clear?
Yes, sir.
Now understand this very carefully, that why YC is much less than Y depth. Why YC is much less than Y depth. Any comment? So one electron giving me minus Q charge, minus 1.602 into 10 raised to minus 19 coulomb, right? And one Na minus ion is giving me how much charge? How much charge it is giving?
Q times Na. Minus Q times Na.
No, it is giving me one electron, right?
Okay, yes, sir.
You got it, right?
Yes, sir.
Because when the purpose of me showing the bond representation yesterday was to make sure that you understand that one boron minus ion is giving me one negative charge, one quanta of negative charge. Is that clear?
Yes, sir.
So that means what? What is the size of the electron?
So it will be in the Fermi meter ranges.
10 raised to minus 15 kind of range, right?
Yes, sir.
And
Fermi
what is the
ranges.
size of the boron atom? Let's say 10 raised to
From
minus 9, 10 raised to minus 10, in this kind of region, right?
yes, sir.
So you see the difference of order of their size, that how much what I need electric field lines from one positive charge here to get terminated at some one quantity of negative charge, right? That is the fundamental principle. My electric field lines has to generate from positive charge and terminate at negative charge. Now the question is that negative charge is being given to me by one electron or one ion, right? So that is
Yes, sir.
why your YC is much less than your Y depletion. Fine.
Hmm.
You will
Yes, sir.
see we will make some approximation called charge sheet approximation. There we consider YC to be 0. Okay. Of course, if it is 5 orders, I can neglect that, right? So that is one of the very key approximations in device physics or device modeling is that charge sheet approximation, where we make this YC tends to 0. This is the reason why we make that approximation, right? Now
Yes, sir.
understand that if I keep increasing my VGB, okay, if you do the analysis, you will see that let's say this charge is QD and this charge is QI. So my QG has to be equal to minus QD plus QI, assuming QOX equal to 0. QG is what? QG is the this gate charges, green colored charges, positive charges. QD is what?
Depletion charge.
QD is my depletion charge and QI is my electrons.
Inversion.
We call it
Inversion
inversion
charge.
charge, right? So this all has to balance because my electric field lines has to generate and terminate, right?
Yes, sir.
If you solve the Poisson equation, you will see that this QD is proportional to square root of surface potential. And by the way, why is my surface potential here? Surface potential, as you have know, we have defined it EC bulk minus EC interface divided by Q. So this surface potential is this. In this case, my surface potential is this. So you see, by increasing the VGB, or if I am increasing my VGB, right? That means this voltage I am increasing. This voltage is getting dropped at psi ox and psi s. This we have discussed yesterday. So this also will have to increase, these two quantity, to satisfy
Yes,
my
sir.
KVL, right? In this
Hmm.
loop. So that is why my psi s is also increasing. And you can see it pictorially, right? Psi s is
Yes.
also increasing. So this QD is proportional to psi s, but your QI is proportional to exponential psi s by some normalization constant, exponential of psi s, right? Now if psi s increases, which quantity will start to dominate? QI or QD?
Sir, QI.
QI will start to dominate, right?
Yes,
That
sir.
means if I change my gate voltage, beyond this point, where my EI and EF are touching, beyond that point my QI will increase exponentially, whereas my QD is increasing square root nature. That means you will see something like this. Let's say this is your psi S and this is your charge S. So you will see your QD is increasing like this and your psi S will increase something like this. So your QI will increase something like this. So your effective resultant will be this, because these are getting added, right? And it is around this point, these two will cross each other. We call this point as onset of inversion, and let's say this is my psi s equal to 2 phi f that we have discussed yesterday, right? And corresponding gate voltage VGB will be equal to threshold voltage. That means threshold voltage is that voltage, that gate to body voltage, beyond which my inversion charge will be much more than my depletion charge. Okay. And what is the consequence? Consequence is that after some time, let's say my VGB is now greater than VTH or threshold voltage. In that case, what will happen in the MOS capacitor? So here are your positive charges, and almost all most of the negative charges will be densed here. There will of course be depletion charges, but you will see that all your field lines are getting terminated at the this magenta inversion charges, right? So this is almost like the similar case where you have a parallel plate capacitor. There will be very few lines that will cross, right? Because the order of magnitude is huge beyond this voltage. One is increasing exponentially with surface potential, another one is increasing square root. So it will be like a parallel plate capacitor, and that is why in inversion you will get capacitance equal to Cox. That will come to later. Okay. So moral of the story is that beyond this point there will be a region, uh, there will be a region which we call depletion, and let's say this is your threshold voltage, corresponding this is 2 phi b. Beyond this we call inversion. Okay, so this is the surface potential real line and this is the VGB gate voltage real line. So for you, till this code, there are multiple further bifurcation of this inversion as well. We will have weak inversion, moderate inversion, strong inversion. But for the time being, you understand that only one junction is there, beyond which it is called inversion. Fine. So we have divided our regions of operation in MOS capacitor into three regions: accumulation, depletion, and inversion. I hope this much is clear, right?
Yes, sir.
So This point is also called onset of inversion. Onset means just about to start. See, this is the same point as this. This is the same point as this, beyond which your inversion charge just start to take control over everything. Fine. So far whatever we have discussed, I hope you will be able to draw the MOS capacitor band diagrams, right? I have only drawn the band diagrams qualitatively. There are some courses in your higher studies where you will learn to draw band diagrams quantitatively. That means this is a 2D diagram, right? This 2D diagram you will be able to numerically measure each and every point. Okay, how much band bending is there? Your metal is not completely like this. Your metal will also have very minuscule bending because there has to be some sheet charge, right? It has some thickness. At room temperature that roams around. That is called metal screening length. That will come from your Debye-Huckel theory and so on, right? But those things are not part of this course. So this understand that this is qualitative understanding. So you need to understand and be able to draw the MOS capacitor band diagrams after this discussion. Okay. If you not, let me know where you are facing difficulty. I have explained you all the steps and all the reasons why it is happening and why it is being drawn like that. Okay. So the question we start, the purpose of discussion was that the questions will follow and you will be able to answer very easily. So the MOS capacitor reaches a threshold when the gate voltage equal to flat band. No, there is no charge at that point. Surface potential equals to bulk potential. Not necessarily. Surface potential equal to bulk potential will happen at which case? What is bulk potential, by the way? Bulk potential is this Fermi level minus EI. This is what we are talking about Q phi F or phi B that we have been discussing, right? So surface potential equal to bulk potential will be at this case where my device is intrinsic, right? In this case, if you see your EC is coming like this, so this is your surface potential Q psi S. Similarly, your EI is will follow. If EI follows, EI band bending will also be same because the distance has to be Eg by 2 at all cases. So this is Q psi S and this is your EF, and this distance at bulk we call it Q phi F or bulk potential. So at this condition, my psi S is equal to phi F or bulk potential. Is that clear? This is just a zoomed version of this. So that is not also the region where we call it as a inversion. The depletion region is fully developed. That is not also true because my depletion region will keep growing, right? Because this
Yes,
is
sir.
my square root size dependency. It never get hard saturated. It keeps growing. Fine. The surface is at the onset of inversion. This is when we consider this onset of inversion. This is my threshold voltage. This is coming by the definition. Okay. Then let's go to the next question. Tell me, flat band condition occurs when surface potential is zero. Is that correct? It is correct, right? We have seen, right? My surface potential is zero at flat band. Then gate voltage is negative, not necessarily true always. It will depend on what your phi ms is, right? We have seen a case when phi m is equal to phi s, my flat band is zero. If my charges inside the oxide is also zero, fine. So gate voltage is negative, that is not always true. The energy bands are flat at the Si-SiO2 interface. That is true. Fine. Why you are calling? Okay. Then the
Yes,
next
sir.
part is there is no depletion region. In case of flat band condition, will we have depletion region? What is the charge inside semiconductor in flat band? E is constant. That means my psi is constant. E is zero. Rho is zero. If rho is zero, no charge inside semiconductor. Right? So for flat band, I do not have depletion region. Fine. Is it okay?
Yes, sir.
Fine. Then next question. Find the N-type NMOS threshold voltage with this. We have seen that threshold voltage formula we write generally as VFB plus 2 phi f plus gamma square root 2 phi f. What is phi f? So what is VFB? VFB is basically your phi ms minus oxide charge
Q
divided by
C
Cox.
of yes, sir.
So Qox is 0. So this part is 0. Phi ms we are not given. We are not given with any information. So we'll consider this 0. So this will be 0. What about phi f? Phi f is calculated as phi t times natural log of Na upon Ni. So phi t at room temperature is how much? Kt by Q.
0.026.
0.026 times natural log of Na is given as 10 raised to 16 and Ni is 1.45 times 10 raised to 10, right? You can calculate it yourself. Then this is also phi f, but we need to know gamma. What is gamma? Gamma is expressed as 2q epsilon Si times Na divided by Cox dash, that is epsilon oxide divided by Tox, and this is 2q epsilon Si times Na. So if we plug in the values, it will be 2 times 1.602 into 10 raised to minus 19. Epsilon Si is how much? 11.7 times 8.854 into 10 raised to minus 14 farad per centimeter. I am in semiconductor physics, we generally deal with all unit in centimeter, right? Centimeter cube, centimeter square and all. So I'll follow that tradition. Then Na is 10 raised to 16. Epsilon ox is how much? 3.9 times 8.854 times 10 raised to minus 14 divide by Tox is how much? Tox is given as 10 nanometer. So 10 into 10 raised to minus 7 centimeter, right? Because we are dealing with centimeters. So those centimeter, if you consider everything in centimeter, so your that unit will you need not to take care later, right? It will get cancelled because ultimately gamma will have some square root of volt unit. Fine. How can you say that gamma unit is square root of volt? What is the unit of VTH?
Volt
What is the unit of this quantity? If it is added, entire quantity.
will also be volt.
So what is the unit of phi f? This is also added, right? It is also volt. So
Yes,
this
sir.
is what? Square root of 2 phi f unit is square root of volt. To have
Hmm.
volt, gamma has to have the unit of square root of volt,
Yes, sir.
right? So this is called dimensional analysis. You can do just a quick check for sanity. So if you calculate, it should come something close to this. Do the calculation yourself, okay? Then what is the relationship between the depletion charge and the substrate doping? Tell me, how should I consider that?
QD is proportional to root NA.
Why? See, that is something answer mugging up of answers. Just tell me the root. How did you tell that? Even or how will you explain it to others that why QD is square root of NA? So QD is this charge, right?
Yes, sir.
So QD is equal to Na, or more precisely Q times Na times W depletion. This dimension is W depletion. Can I write that? This is per unit area, okay? Let me write it in different way. So QD is composed of what? Na minus ions, right? Composed of Na minus ions. Is that clear?
Yes, sir.
So what is the concentration? Concentration is charge times concentration is Na. This is the doping concentration. Now I need to take care of the geometry. What is the unit of this? Unit of this is Coulomb
Centimeter.
per
Coulomb per centimeter
centimeter
cube.
cube. So to get the entire charge, I need to multiply it with the dimension. What is the volume of the charge? L times W depth.
Yes, sir.
Okay, let us be consistent. Y depth we are using, right? Is that clear?
Yes, sir.
So Q, and this is centimeter cube. So entire thing will come out to be coulomb. So Q times Na times L times W times Y depth. What is the equation of Y depth? What is the equation of depletion width of a PN junction?
So square root of 2 epsilon s by E
2
in this
epsilon S divided by
divided
QNA, the
in
weaker
this
dope
voltage
direction, times the reverse
voltage.
bias voltage plus break the built-in voltage.
Yes, sir.
In this case, you will have surface potential.
Yes.
Okay, is that clear?
Yes, sir.
Fine. So what is the dependency on f of Na, or how will it vary with Na? One is Na, then another there is square root of Na, right?
Yes,
This
sir.
will give you square root of Na dependency.
Hmm.
Is that clear? So
Yes,
in
sir.
now you don't need to remember how this formula of QD and what not, right? You just need to remember your PN junction concept and just work your way through to the dimensions and you get your answer. Okay. Then
Yes, sir.
next is, how does increase in substrate doping concentration affect MOS capacity? I think we have done this question yesterday. So VTH increases, right?
Yes, sir.
VTH is equal to VAB plus 2 phi F plus gamma square root of 2 phi F. So gamma is square root 2 Q epsilon S Na divided by Cox dash, right? And your phi F will also have natural log of Na by Ni. We have shown yesterday that natural log has a weaker dependency than this square root. Fine. So the square root will dominate. So gamma is the main factor that determines the substrate dependency. And of course, from the equation, you can tell that it is increasing. Then next question is, which of the following statement about the PMOS transistor is incorrect? Threshold voltage is negative, generally true. So PMOS transistor means what will be the doping of the source and drain?
P plus.
And this is N, right? N type substrate. PMOS means holes taking
Formations on it.
part into conduction. So for a hole reach area to another hole reach area conduction to happen, this has to have a layer of holes. That will happen when this N type will get inverted. So substrate is P type. This is incorrect. Inversion layer or induced layer is of P type. That is true. This is also true generally. Just how we analyzed your NMOS, if you check your in case of PMOS, you will get to know that it is just the opposite sign. However, we have assumed that your phi ms and all is, phi ms is equal to 0 and all. That may create a little bit of offset your flat band voltage. Otherwise, you will see that your PMOS will have a negative threshold voltage. And that is of course true, right? If you have your negative charges here, then only this dopant will get ionized and holes will start to generate, and in this case your electric fields will be in this direction, upward direction. Okay, so none of the above is not true, so this is incorrect. Fine. So moving on to the next question. The mobility of the hole is, tell me this one. By the way, what is mobility? Have you seen something like this equation?
Yes,
Ease
sir.
of movement of free carriers in any material. So why can't we have infinite mobility? Why can't we have infinite mobility? It is controlled by the random event called scattering. So scattering can be of many types. Carrier scattering, impurity ion scattering, then you will have lattice vibration scattering, then you will have scattering due to interstitial void atoms, then you can have grain boundary scattering, and another important thing is your, in case of MOSFET, is your surface roughness scattering. Okay, fine. Scatterers means, suppose you are going uh, let's say at 80 kilometer per hour, you are riding your motorcycle. The friction with the this your, how do I put it, on the road with the tires of the motorcycle is one type of scattering. Similarly, let's say you feel hungry, you get stop at some food shop, right, or some restaurant. There you will have some perturbation in the motion of your motorcycle, that creates another kind of scattering. So similarly, when electrons or holes move around in the semiconductor or the crystal, it sees multiple type of disturbances or distractions, which causes a temporary halt to their flow, thus not allowing it to attain infinite mobility. Okay, so this Q is the charge, m is the effective mass, tau is the mean time between scattering. Okay, basically your electrons will move like random thermal motion. Okay, at any given temperature. So at each point this, where it is changing its direction, it encounters one scatterer. Okay, this is when we do not have any electric field applied to it. So it is just moving around with some random thermal velocity. Now if you apply some electric field, what you see that if your electric field is in this direction, your electron generally move into this direction. But electron does not move into a single line. Due to a random thermal motion, it will keep getting scattered, but the average sense of the electron will move toward the electric field, opposite toward the electric field, right? So electron moves like this only. Electron does not move in a single line. And these events, scattering events, determine how good a conductor you have, right? You know your resistance is equal to rho L by A. What is this rho? Rho is 1 over sigma or conductivity. What is this conductivity? This is your Q mu times your doping concentration, right? If I only talk
Yes, sir.
about electron. Fine. So if you have higher mobility, you will have, if you have higher mobility, you will have higher sigma, you will have lower rho, you will have lower resistance, or your flow of current will be more easier. Fine. In semiconductors, we have two most important kind of phenomena, scattering phenomena that determines the mobility. In case of bulk semiconductor, I am no, bulk means it is one single block. In if you are at any atom, if you look at any direction, you will see the similar kind of arrangement. What about interface or junction? You will see a different arrangement after the wall, right? Or the potential barrier, there will be some barrier. This all are the same thing but different representations. Fine. So the important thing is this one, impurity ion scattering, this one, lattice vibration scattering, and this is important for MOSFETs. Why it is important? Because you know that carriers are moving. Let's say this is a wall. Okay, let's say this is a wall. One runner is running just very close to the wall, right? And the same guy running in a clear field. So in which case its uh, speed or movability will be smoother? Of course, where there is no distraction or no hindrance, right? If he is running very close to a wall or the interface, it will see different kind of distractions or scattering events, right? So that is why surface roughness scattering becomes important in case of MOSFETs. But in case of bulk semiconductors, where the transport is throughout the device, not at any confined to any interface, in that case, these two dominates. Impurity ion scattering, this is also called Coulomb scattering, and this is also called phonon scattering. So what is the difference? Let's say you have a charged ion, right? Let's say this is Nd plus. One ion is sitting there. One free electron is moving freely from one place to another place. So if there is a positive charge sitting here, of course its path will get deviated due to Coulombic attraction, right? So this creates a scattering event. Okay. So this scattering is called Coulomb, or sometimes more rudimentary name is Rutherford scattering. So what will happen if you increase the temperature? Why was this electron moving? Electron was moving due to its random thermal velocity. So if you increase temperature, so VTH or thermal velocity of the electron will increase. So it is more less it is less likely to get scattered to the ionized charges. It may be positive or negative. If it is negative, let's say if it is negative charges, electron will just go in this direction. Fine, it will get repelled. That is also Coulombic repulsion force. So if your temperature is more, less scattering, that means your mobility will be higher. Okay, and this Coulombic scattering mobility is determined, is basically proportional to temperature raised to minus 3 by 2. Fine. So I will draw a plot of temperature versus mobility. So your Coulombic scattering is something like this. If your temperature increases, mobility increases. This is log scale, remember. So that is why my power law gets become this, right? So this is increasing, right? This will be positive. If temperature increases, mobility increases. Another thing is that this phonon scattering, what is happening? Let's say you have a silicon atom and your temperature is not equal to 0 Kelvin. It has some temperature. So what will happen? The silicon atom will vibrate around this lattice point, and that creates two with something that creates two elastic waves from wave particle duality. This also can be considered as some particle. We call it phonons. These are the same particles that are responsible for carrying voice over the air medium from one place to another, right? So these are called phonons, similar to photons. Photon carries light, phonons carries sound. You can understand, remember in this sense. So what happens? If your temperature increases, the vibration will also increase. That means more number of more number of phonons. That means more number of scattering events. So lesser the mobility. Fine. So in this case, mobility is inversely proportional to your temperature. Fine. So that line you generally draw like this. So this is your Coulomb scattering. This is your phonon or lattice scattering. Fine. Now you might be aware of the Matheson rule. So this is what resistances in parallel. So the lesser one will dominate. Fine. So your final mobility versus temperature curve, you will get something like this. The lower the line, it will dominate. Fine. So this rule is called Matheson's rule. Okay. So now if we ask you that whether with temperature mobility increases or decreases, you are not able to answer. Fine. Because it has both the phenomena depending upon what temperature range we are talking about. Fine. Remember that in case of silicon, this is the place where your room temperature lies. Fine. This is one of the important phenomena why our semiconductor industry was successful, because we wanted to change the resistivity of the semiconductor by doping and not some random fluctuation in the temperature. Fine. Otherwise, what would happen? Suppose your smartphone is working in summer, will not work in winter. The performance will be way too different, right? Because your room temperature applications, mobility is fairly constant around this region. That is why this N or the doping will allow me to control the resistivity of the semiconductors. Fine. So if somebody asks you that with temperature how the mobility of hole or electron changes, so what you should ask first, at what temperature you are talking about, or we are discussing, we are concerned about. If it is room temperature, beyond room temperature in silicon, mobility drops, right? Now if I tell you that no, tell me at around cryogenic some low temperature, let's say 77 Kelvin, then of course the temperature mobility increases, right? Due to Coulomb scattering, because phonon scattering is not dominated at that time yet. Okay, so that is why you answer the answer of this, you may say that decreases with increasing temperature. That is true considering T0 is at room temperature. That means at which position you are standing. You are standing at here or you are standing at here. Depending upon that, your answer will change. Right? Any question on that? Otherwise, we will close today. Anyone? Okay. If no, then we'll close today and see you next week. Thank you for
Thank you, sir.
joining. Yeah.